Hi guys, we're back to talk about soil density. So as always, let me share my screen here. Okay, so density in general, I find is a concept that sometimes people misunderstand. So density is not the same as weight. It's not how heavy something is, but it's basically how massive, which we can sort of measure as how heavy something is, how much weight it has, per unit mass. So for a particular mass, how much weight do we have in that with that particular amount of stuff? So we could have something that's very heavy, like something that's very large and heavy that we would put on a scale that could actually be much less dense than something that weighs less, like a little nugget of gold or something. That little nugget of gold might be small and weigh less than a table, but it might be more dense because for the amount of stuff, it's really packed into a small space. So it's this relationship between space and mass, which we basically measure as like space and weight. And that's really what density is all about. So we can measure two kinds of density in the soil. We can measure particle density and then we can measure bulk density. So bulk density is really a more important measure that we're going to mostly focus on. But first, when we measure bulk density, we need to know particle density. So particle density is the density of the actual just soil solids. So if you have a little grain of sand, that's basically a little bit of rock, and you can actually just measure how dense is that rock. Another way to think about it would be like if you could take the soil and remove all the airspace and just completely pack it down, which is not logistically possible, so that there's no space. And so you just had a big clump of all the soil solids with no space, with no water, and you measured the density of that material, that should pretty much give you the same density as if you zoomed in more finely and measured the density of like the soil or silt particle itself. And in most cases, that actually is a very consistent density. The density of most rocks is around 2.65 or 2.7 grams per cubic centimeter. So a cubic centimeter is about the size of like a sugar cube. And so for that size of material, you would expect the soil particles to weigh about 2.7 grams. And so that's particle density. But of course, in the environment, soil is not just particles. Soil is this complex ecosystem with lots of organisms, with lots of pore space, with plant roots, with fungal hyphae, with aggregates, with macropores, micropores. And so the actual density of the soil in its natural environment is going to be really different than that particle density. And it's going to be a lot lower because there's going to be a lot of air and other space in there. And so that real soil in its like natural structure density is what we call bulk density. And that of course varies across soil types and soil management. Again, it's always going to be less than just like the density of straight up rock, which is again about 2.7 grams per cubic centimeter. And so we're going to be able to measure that as the mass of dry soil divided by the volume, the space that the soil takes up. So here's kind of soil in its natural form, bulk density, as opposed to what would just like the particles themselves weigh based on how much space they would take up, based on how much does that same amount of stuff weigh compared to how much space it actually takes up in its soil environment. So the particle density is always going to be more dense compared to this. Okay, so what are things that affect bulk density? Well, soil depth. So often deeper down in the soil is less aggregated. And as soil forms these aggregates, as we saw before, it provides pathways for larger size pores because the bigger pieces can't like fit together as tightly. There's going to be bigger channels in between the bigger pieces, which as opposed to if you just have a lot of fine clay particles, they can really bump up next to each other very closely and there's not a lot of big spaces in between. So because there's less organic matter, because there's less aggregation down low, we tend to have denser value or higher bulk density values down low compared to up high. And then of course, soil management or land management decisions can affect this a lot. So compaction of the soil is basically where we have something that's very heavy that pushes down on the soil, and then that is going to reduce the spacing in between the soil and make it more dense. So if you're driving heavy equipment over the soil, if you're driving even not that heavy equipment over the soil, especially when it's wet and more flexible, not as strong, we'll talk more about that later. So you can see when people drive on dirt roads during like the fall time or the winter time or the early spring, when it's wet, they do a lot more damage to roads. They get big ruts in the roads, whether that's like with bikes or with OHV or trucks or cars, whatever, or of course heavy equipment too, then that's going to lead to a much more soil compaction. And then again, it doesn't necessarily have to be something big. If you walk over the soil a lot, if you ride your bike over the soil a lot, if you ride your horse over the soil a lot, that kind of repeated compacting of the soil can reduce the pore spaces and can push the particles closer together, which increases soil bulk density, which might have certain values, but is not going to be as good for supporting plant growth. And then other things that would reduce density are things that break down soil aggregates. And so this can relate to soil disturbance. So if we're really doing lots of aggressive tilling of the soil and different kinds of mechanical disturbance, which may be intentional tilling for agriculture, but maybe other kinds of processes, that can break down the soil aggregates. And once the soil aggregates are broken apart, then they can actually fall back together in a more compacted structure. And so they actually become more dense once they're broken up, which sometimes people find a little bit counterintuitive. Okay, so thinking about these soil aggregates that we mentioned last time and thinking about how they're arranged, it's going to, of course, impact the density of the soil and its environment. And so we talked about the fact that very rarely do individual soil particles actually act as individuals, but they're often clumped together, especially in a healthy soil. And so as they clump together, we have aggregates, and within those aggregates, there's going to be tiny little spaces. Those are called micropores. And then in between the aggregates, we're going to have bigger spaces that can facilitate the movement of water and air. And those are called macropores. So the macropores are much more important in terms of facilitating water and air movement around in the soil. But micropores can also contribute or influence density in the same way that macropores can. So in general, when a soil has a low density, there's not a lot of material packed into a small space. It has a low density because it has lots of pore space. A lot of the area in the soil is just space without any solids in it. Whereas on the other extreme, if we have a high density soil, we have lots of material packed into a small space, then guess what? There's just not a lot of space left. So it has a low percentage of pore space. But as I said, not all spaces are created equal. So it is possible to have a soil with decent total pore space, but if a lot of that pore space is made up from micropores and there's not a lot of macropores present, then that can influence the way that the soil is actually functioning. And we'll talk more about that later. But the pores are important to hold both water and air. They're both important. Soils and soil organisms need both. And in general, remember, the macropores are going to be more important at moving water and air around the soil to get to organisms. Besides bacteria. Bacteria can get into the micropore areas and access it, but most other organisms can't. Okay, so here is some ways to think about soil texture. This is some beautiful original drawings by yours truly. So in picture A, what I have are dispersed clays and silts. So this is a soil where there's not much soil aggregation. So maybe due to extended periods of aggressive tilling and mechanical disturbance through limited organic matter. For whatever reason, these soils are not aggregating well. and they're not flocculating well. So as these small pieces kind of are, if not completely individual, in very, very small groups, as they're fitting together, because they're so small, they can actually fit together pretty tightly. And so you'll see micropores in this environment, but not a lot of macropores due to the lack of soil aggregation. So in this case, we're going to have pretty high density soil. So there's going to be some pore space, but it's going to be somewhat limited because there's really only micropores. There's not any big macropores. Okay, the next example is sand. So sand has bigger soil particles. They also don't aggregate very well, but because they're pretty big, they don't fit together as tightly as clays and silts can. So there ends up being bigger spaces between them just because they can't fit as neatly, as tightly together as the smaller pieces can. So in this case, there's going to be macropores present, but there's not going to be many micropores present. So there's some porosity, but not as much porosity as we might find in some different soils that we'll talk about next. So in this case, we're going to have moderate density and moderate porosity soils. Okay, then loams. Remember, loams are those soils that have a mixture of sand, silt, and clay, all the different soil particle types. And so in this case, if those loams are healthy loams that are able to form aggregates due to the presence of organic matter, limited soil disturbance, healthy soil fungal communities, etc., then you'll see some little aggregates forming. So my picture C is supposed to show some different size soils grouping up together. And in this case, you'll have macropores and some micropores, okay? So you'll have not too dense and not and fairly good pores, so pretty decent, or middle of the road density and middle of the road porosity. And then finally, loams or other soils that are really high in organic matter and have lots of clay. So this might be like a clayey loam, or just a loam that really has lots of good organic matter that has really great aggregation. So hopefully you can see the difference between image C and image D is that the soil particles in image D are supposed to be much more tightly clumped together in bigger aggregates. At least hopefully that's what I was trying to show with my beautiful illustration here. And in that case, you're going to have micropores because there's pores inside the soil aggregates, and probably more micropores than you had in C. And you're going to have really nice macropores because these bigger aggregates like the sand and B can't fit together very well. So there's pretty big spaces in between them. So this is where you're going to get your lowest density and highest porosity soils. Okay, so the more soil aggregation you have, the lower your soil bulk density is going to be. So that's something to keep in mind. So at first, some people might think, oh, well, clay particles can all fit together really well because they're so small. So that would be like in A. And that's true. And if the soil is disturbed by mechanical or chemical means, if it has been kind of broken down so the individual particles are not aggregating well, then that soil might have pretty high density. But if the soil is functioning well, and it's in a healthy environment, has good organisms and good organic matter, et cetera, and it's being well aggregated, then that soil that has these fine particles might actually have a pretty low density and even a lower density than something like a sand. So anyway, I think hopefully this drawing will help you kind of understand the different kinds of factors that contribute to bulk density and porosity. And in general, as density goes up, porosity goes down. So the denser you have, the denser you are, the less pore space you have. Okay, here's a figure from the text showing BD or bulk density values. So as I said, particle density values for rocks that break down to make soil are usually about 2.6, 2.7 grams per cubic centimeter. Soils are always going to be less than that because they're always going to have some amount of pore space in them. And those that have like an incredible amount of organic matter, like histosols, are going to have really low bulk densities. And then andisols, which are made of this really fluffy volcanic ash material, are also going to have very low bulk densities. And then as we get down here to more clay-like soils, et cetera, we're going to start to have some more higher bulk densities. And remember, the soils, if they have good clay soils, if they have good organic matter and good aggregation, they might have slightly more moderate densities. And then if they're not well aggregated, that's when we're going to see the highest soil bulk densities. So anyway, this range, like 1.2, 1.3 is going to be kind of a middle of the road. 1.2, 1.3 grams per cubic centimeter is going to be a middle of the road soil bulk density. So I'll make you do some problems, and that would be something to keep in mind. Okay, so how does soil aggregate affect drainage? Something I've mentioned a couple of times. Well, basically, the better and stronger the aggregates are, the bigger the spaces between the aggregates are going to be, which is going to facilitate better soil drainage. And so sometimes we don't want to have our soils drain so quickly that the water really moves away from the plant root environment so fast. But on the other hand, we really want soils to be able to drain fairly effectively so that they are able to absorb water in a rain event, especially if we live in an environment where it doesn't rain that many days of the year in a place like California. So when it rains, we don't want the soil to only be able to absorb, half an inch of rainfall and then have all the rest of the water just be flowing across the surface, kind of like a sheet flow, which one is going to lead to erosion, but also is just going to limit the amount of water that's available in the soil later on after it stops raining. We really want that soil to be able to act like a sponge and be soaking up and moving water away from the surface to accommodate more water. And aggregates are the name of the game. So over here, in this example on the left, we have soils that are, again, not well aggregated. They're broken down into smaller pieces that are fitting more tightly together. So the higher density, lower porosity version, kind of like the picture A that I showed you before. And so when it rains, there's some small spaces. Some water can be absorbed by the soil, but pretty quickly the soil is going to be overwhelmed. And instead of water going down into the soil, the water is going to run across the surface. That could lead to things like flash flooding, but it could also lead to the removal of soil surface particles, soil erosion, and certainly is going to limit the amount of water that's going to be stored in the soil at the end of this storm event. On the other end, we have more stable soil aggregates, healthy soil aggregates from calcium, polyvalent cations, organic matter, healthy fungal populations. Then we're going to have these big spaces that water is going to be able to move into. And so it's going to be able to move down into the soil away from the surface quickly to accommodate more and more and more water absorption during the same storm event. So that's going to limit erosion, limit flash flooding, and it's going to increase the water storage in the soil. So then maybe if it doesn't rain again for weeks or months, there's going to be a big reserve of water that's stored in the soil that plants and other organisms can draw on later on. So in this way, aggregation is really a really important factor in a lot of healthy ecosystems. Okay, that's a good stopping point.